So let's do a review of yesterday, right? Composite functions. So if f of x is equal to the square root of x plus 5 and g of x is equal to x squared plus 1, okay, then h of x, which is the composite of f with g as a function of x, is defined to be equal to f of g of x. G of x is the inner function, f of x is the outer function. G of x is inside f of x. So to find f of g of x, we replace g of x with what it's equal to. It's equal to x squared plus 1. And then to evaluate f of x squared plus 1, you plug in x squared plus 1 where we see an x on the right-hand side of f of x. So this is equal to the square root of x squared plus 1 plus 5, which simplifies to the square root of x squared plus 6. Okay. We're doing this in pre-calculus now. So hopefully, I remember seeing composite functions on my ACT math test my senior year when I took the ACT test back in Iowa. So hopefully, right, for those of you placed in here out of high school, right, you saw this in high school. All right, and now that's composition. Now let's review decomposition, because that's what we need for the, we need composition for the chain rule. Okay. So we're going to find two functions, f of x and g of x, such that the function h of x is equal to the composition of f with g as a function of x, which by definition is equal to f of g of x. If h of x is equal to the quadratic function 2x squared plus 4x plus 7. G of x is the inner function, f of x is the outer function. Isn't it obvious? What the inner function is? It is?
I think so.
What is it?
2x squared plus 4x.
You know what? That works, doesn't it? 2x squared plus 4x. You could write that as your inner function, right? And then you replace 2x squared 4x with x, and you're left with the outer function x plus 7, right? It's not necessarily two simpler functions, right? Going from this to this, but it works, right? It does work, right? Yeah, I'm sort of being a wise guy because we're covering quadratic functions in pre-calculus, and those of you who took pre-calc from me, we did this, and that you can rewrite a This is ax squared plus bx plus c form, their standard form. And so if you rewrite this quadratic function standard form, it's 2 times x plus 1 squared plus 5. So then you could use, right? Remember the vertex for a quadratic function? This number tells you where the vertex is in the parabola, graph of the parabola, right? It's at minus 1, 5, okay? And the parabola opens up, okay? So you could let g of x equal x plus 1 squared, and then f of x would be equal to 2x plus 5, right? That would be two simpler functions, right? Yeah, I'm sort of being a wise guy, right? If we weren't covering this in pre-calc right now, I wouldn't have done that too, okay? But you get the idea about composition and decomposition. That's the main goal here, right? To remind you about composition and decomposition, okay? All right. So let's talk about the derivative of a composition function. And we are not going to give a proof. The proof of what's called the chain rule, right? Derivative of a composition function is in the textbook. And it's basically an epsilon delta proof. So if you want to see the proof of the chain rule, you can read it in the textbook. Okay. So we're going to state it without proof. So we have h of x is equal to f of g of x. The derivative of that composition function h of x is h prime of x, and that's equal to f prime. Now remember, f of g of x, right? This is the function f being evaluated at g of x. And so h prime of x is equal to f prime of g of x times g prime of x. So up here we evaluate the function f at g of x. Down here we evaluate the derivative of f prime at g of x. And then we multiply that derivative by g prime of x, derivative of the inner function. Okay. So g of x, again, is the inner function, and f of x is the outer function. I saw the fire department roaming around the hallway, so I don't know if that's them making a noise or
They
what.
took some girl out on a stretcher.
Oh, really?
Mm-hmm.
Is she passed out, or?
I just looked over.
It's usually what happens to
She looked at it.
people with gray hair. Okay? So, and this derivative is known as the chain rule. And later on we'll find out the reason it's called chain rule is right now we're just taking the composition of 2 functions, but you can take the composition of 3 functions, 4 functions, 5 functions, 6 functions, 7 functions, and so forth. Okay. All right, then you can differentiate them. So in this first exercise, we're going to find the derivative of the composite function h of x is equal to the square root of x squared plus 1. Now, just as a side note, this is equal to x squared plus 1 raised to the 1/2 power, right? And so if we were differentiating the function r of x equals x to the 1/2 power, you know that derivative is equal to 1/2 times x to the minus 1/2 power, right, by the power rule. So you might be half tempted to think this derivative, right, you bring the 1/2 down front and then subtract 1 from the exponent and you're done. But that's not the case, okay? There's more work to be done. All right. So h of x can be decomposed, right, into the composition of two functions, where the outer function f of x is equal to the square root of x, and the inner function g of x is equal to x squared plus 1, right? When you take the composition of f with g, you end up with square root of x squared plus 1, right? So this is our decomposition. Decompose. Good thing I wasn't an English major. Okay. All right. Well, f prime of x, we just showed it over there, right? This is x to the 1/2. F prime of x is equal to 1/2 times x to the minus 1/2, which is equal to 1 over 2 times the square root of x, right? And g prime of x, right, we're just using the rules. Right now, we're just using the rules of differentiation, 3.1, right? The derivative of g of x, derivative of x squared is 2x, derivative plus 1 is 0, right? So plugging in over here for h prime of x, h prime of x is equal to f prime evaluated at g of x times g prime of x. Well, f prime is equal to 1 over 2 times the square root of x, right? And now we evaluate f prime at g of x. What's g of x? X squared plus 1. Well, let's fill it in, right? So this is f prime evaluated at x squared plus 1. Right? That's what g of x is equal to, right? X squared plus 1. And then g prime of x is equal to 2x. Now we evaluate f prime at x squared plus 1. How do we do that? We put x squared plus 1 in wherever we see an x on the right-hand side of f prime of x. And so this is equal to 1 over 2 times the square root of x squared plus 1 times 2x. Now you can see multiplication by 2 undoes the division by 2. And so when we multiply x times this fraction, we have the derivative of h of x, h prime of x, is equal to x over the square root of x squared plus 1. And so that is the derivative of h of x by the chain rule. Okay? Derivative of that composite function. Any questions on that? Okay. So to use this, right, you gotta break down, figure out what the inner function is, what is the outer function, and you have the rules of differentiating of the inner, the outer function. All right, let's do another. Let's find the derivative of the composite function h of x is equal to 5x to the 6th, 5x to the 6th plus 2x cubed raised to the 4th power. Now again, right back in section 3.1, if I had the function r of x is equal to x to the 4th power, we know by the power rule that derivative is equal to 4x cubed. So you might be tempted in differentiating this, bring the 4 down in front of the left parentheses, subtract on the exponent, and then stop. But there's more to the derivative than that. That's half the derivative, but there's another half, okay? So this decomposes into f of x is equal to x to the 4th, and g of x is equal to 5x to the 6th plus 2x cubed. So when you take the composite of f with g, you end up with h of x up here, right? This is the inner function. When you place x with the inner function, you end up with h of x up here, okay? Now f prime of x from section 3.1, right, we just pointed out, is equal to 4x cubed. And g prime of x, I'm going to differentiate term by term, right? Derivative 5 is a multiplicative constant. Derivative of x to the 6 is 6 times x to the 5th. So we have 30 times x to the 5th. And then derivative of x cubed is 3x squared. So we have 6x squared. Right, so g prime of x is equal to 30 times x to the 5th plus 6x squared. So plugging in, we have, so plugging in, we have f prime evaluated at g of x, and g of x is 5x to the 6th plus 2x cubed. And then we multiply that times g prime of x, and g prime of x is that binomial, 30 times x to the 5th plus 6x squared, right? You gotta put it in parentheses. Otherwise, you only multiply by the first term. Okay. Are you with me so far? Am I losing you? If I'm losing you, say something so we can back up and review. Okay. So f prime evaluated at 5x to the 6 plus 2x cubed. We put 5x6 plus 2x cubed in for x on the right-hand side of f prime of x. And so we have 4 times 5x to the 6th plus 2x cubed raised to the 3rd power times 30 times x to the 5th plus 6x squared. That's h prime of x. So this is the derivative of the h of x over here. Okay? Any questions? Nada? Okay. All right. So this is application of the chain rule used in what is called prime notation. right, or function notation. But you remember there's that guy by the name of Leibniz, in Germany, who developed calculus at the same time as Sir Isaac Newton in England. So that's, right, he came up with the derivative of a composite function, right? He came up with the chain rule using his notation. So we're going to do these two derivatives over again using Leibniz notation, okay? All right, so you know y values and function values are the same thing, right? So we can write h is a function of x, so we can write y is equal to h of x. And h of x, right, is a composite of f with g, right, as a function of x. So we replace h of x here with y. We have y is equal to the composite of f with g, okay? Y is a function of x, okay, as well. All right. I'm just going to rewrite what I wrote here, up here, because I need a couple of columns. All right. We're going to substitute u. We're going to set the letter u, the variable u, equal to g of x, right? Just like we set y equal to f of x, we're going to set u equal to g of x. So in function notation, right, x is the independent variable, u is the dependent variable, right? X is the input, u is the output, okay? Just like with x and y, okay? When we make that substitution, then the derivative of u with respect to x is equal to g prime of x, right? Derivative of u with respect to x is equal to the derivative of g of x with respect to x, which we denote with g prime of x. Okay. When we replace g of x here with u, we now have y is equal to f of u, right? F is a function of u. When we replace g of x with u, right, y is equal to f of u, y is now a function of u, okay? And the derivative of y with respect to u is equal to the derivative of f with respect to u, which is f prime of u, okay? So the derivative, going back to our composite function, the derivative of y with respect to x from the definition of derivative of composite function, right, is equal to f prime of g of x times g prime of x, right? That's the definition of derivative of composite function on the right-hand side. Okay. Well, this on the right-hand side, f prime of g of x times g prime of x. If I replace, remember, u is equal to g of x, so if I replace g of x with u, I have f prime of u, right? This is equal to f prime of u. And g prime of x is equal to the derivative of u with respect to x. F prime of u is equal to the derivative of y with respect to u. So I'm going to replace f prime of u with derivative of y with respect to u. So we have the derivative of y with respect to x, or with respect to u, times the derivative of u with respect to x. So I can replace f prime of gx times g prime of gx with the derivative of y with respect to u times the derivative of u with respect to x. This is the derivative of a composite function using Leibniz notation. Okay. Derivative of y with respect to x is equal to derivative of y with respect to u times the derivative of u with respect to x. Okay. Now, what makes Leibniz notation easy to memorize is these two derivatives. They look like fractions, right? Quotients, but they're not. But they look like it, right? We've got a numerator and denominator. When you multiply two fractions, and you got a common factor in the numerator and denominator, you can cancel them, right? So if we treated this product on the right-hand side like fractions, the du's would cancel, and we'd be left with dy over dx. So that's what makes Leibniz notation sometimes easy to remember. Is that once you cancel out all the common factors on the right-hand side, you got to end up with dy over dx. Okay. All right. So let's see how this works in practice with the previous two examples we did. So in the first example, right, we're going to find the derivative of y with respect to x of the composite function y equals the square root of x squared plus 1. Okay? Now we already found that derivative, but we're going to do it now using Leibniz notation. Okay? So remember u, we set u equal to the inner function. And the inner function in this case is x squared plus 1, right? U is equal to g of x, the inner function. Okay. So if u is equal to that, then the derivative of u with respect to x is equal to 2x, right? Derivative of x squared is 2x and derivative plus 1 is 0. Okay. When we replace x squared plus 1 up here with u, we end up with y is equal to the square root of u, which is u to the 1/2. Then the derivative of y with respect to u, right, using the power rule, bring the 1/2 down from the u, subtract 1 from the x1. Remember, we're differentiating with respect to u, not x. So when we differentiate with respect to u, we do that differentiation just like we would when we were differentiating with respect to x, and there was an x here. Okay. So derivative of y with respect to u is equal to 1/2 times u to the minus 1/2, which simplifies to 1 over 2 times the square root of u. So the derivative of y with respect to x, which is what we're trying to find, is equal to the derivative of y with respect to u times the derivative of u with respect to x. Well, derivative of y with respect to u is 1 over 2 times the square root of u. And the derivative of u with respect to x is equal to 2x. And so, again, you can see the 2's cancel. And then when you multiply these, you got 1 times x, which is x in the numerator. And the denominator, you got the square root of u. And what's u? U is equal to x squared plus 1. So you put x squared plus 1 in for u. And so we have the derivative of y with respect to x is equal to x over the square root of x squared plus 1. Okay? So you got to do a reverse substitution at this step, right? Replace u with what you set it equal to. And you end up now with the same derivative as when we did it with prime notation. Okay? Are you with me? All right, so let's take a look at the next one. We have y is equal to 5x to the 6 plus 2x cubed to the 4th. Okay? So remember, u is equal to the inner function, right? And the inner function is 5x to the 6 plus 2x cubed. So u is equal to 5x to the 6 plus 2x cubed, right? That's the inner function. Now the derivative of u with respect to x, right? Derivative 5x to the 6 is 30 times x to the 5th. And the derivative of 2 times x cubed is 6x squared. Now since this is equal to, we set this, that's our inner function that was set equal to u. Y is equal to u to the 4th, right? And if y is equal to u to the 4th, the derivative of y with respect to u is equal to 4u cubed, right? And now we have everything we need to find the derivative in Leibniz notation. Okay? The derivative of y with respect to x is equal to the derivative of y with respect to u, which is equal to 4u cubed. And then we multiply that by the derivative of u with respect to x, which is 30 x to the 5th plus 6x squared. And now we replace u with what it's equal to. What's u equal to? 5x to the 6 plus 2x cubed. So derivative of y with respect to x is equal to 4 times 5x to the 6 plus 2x cubed raised to the 3rd power times this here in parentheses. 30 times x to the 5th plus 6x squared. Right, that is the derivative. The y equals 5x to 6 plus 2x cubed to the 4th power. Any questions? Will you be given a bunch of functions on exam 2 and have to differentiate them? Like this? Yes. Alright.
You're gonna be super mean and ask us
Oh.
to switch between.
You wouldn't
Units
believe the
and-
functions that I come up with in my dreams. Okay? I mean, it'll be, it'll test whether you know the rules of differentiation, but I don't intend to make it something super vile.
I meant more like.
But
which
the
notation
examples
we
that I do
use,
in class, right, they're fair game for exam questions, right? Yeah. So anything I do in class, right, is, and what you see in the website homework, I would say is fair game, okay, at that level. Okay. All right. All right, so any question on prime notation? Leibniz notation. So technically speaking, when you come listed, you're told to use some sort of form of notation. You get to choose, right? Do you want to use prime notation? Do you want to use Leibniz notation, right? Choice is yours unless you're instructed otherwise, right? Well, at the end of the day, you know, just like we had the limit laws, right? We know the limit laws, but we don't actually write them out when we're finding the limits. And then in sections 3.1 and 3.2 and 3.3, we learn rules of differentiation. We know what they are, but we don't actually write them out when we're differentiating. Sort of same thing with the chain rule, okay? We've been breaking it down, right? Defining what g of x is, what u is, right? What f of x is, and all this stuff. But when it comes to applying the chain rule, right, you don't have to write down all this stuff that we're doing, okay? We're just sort of proving it, right? We're just breaking it down to show how you use the chain rule. But when it comes to actually doing the derivatives, I give you some function and ask you for the derivative, you don't have to write all this stuff down, right? I just want to know what the derivative is. What's dy over dx, okay? And so you apply a lot of the application up here, okay, in writing out the answer. So let's come up with some formulas. Because there are patterns in applying the chain rule, just like there are patterns in everything else in calculus. Okay. So let's remember the power rule. N is any real number. So this is going back to section 3.1. Okay. N is any real number. Then the derivative with respect to x of x to the nth power is equal to n times x to the n minus 1 power. Okay? Everybody agree with me on that? I should have brought extra chalk today. Let's see if yellow works. All right. So given this information, okay, does yellow show up good? Can you see that? Can you see the yellow? Okay. So we're going to find h prime of x if h of x is equal to, now instead of x to the nth power, we're going to have a function of x to the nth power, okay? So we're gonna have g of x raised to the nth power, okay? Not x to the n, a function of x to the n power, okay? So to do this, right, we're gonna decompose our function on the right-hand side here, okay? F of x, the outer function is x to the n, like up here. And g of x is the inner function. That means function. F to the n means function, okay? So I'm just specifying that g of x is some inner function. I'm not saying given its algebraic representation. It's any differentiable inner function, okay? So we got g of x raised to the nth power. And so the composition of f with g is equal to, right, when you put g of x in for x here, you end up with g of x to the nth power, okay? And when we do this decomposition, well, let me write this out just so that we understand this. H of x, right, is the composition f of g of x, which is equal to, when you put g of x in for x at x to the n, right, you have g of x to the nth power, right? So h of x is indeed a composition of f with g, okay? Now, f prime of x, in this case, f of x is equal to x to the n, so by the power rule, f prime of x is equal to n times x to the n minus 1 power, right? Bring the n down front, subtract 1 from the exponent, okay? So h, using prime notation, h prime of x is equal to f prime evaluated at g of x times g prime of x, right? That's derivative of this, of a composite function, right, known as the chain rule, okay? Well, f prime is equal to, f prime of x equal to n times x to the n minus 1. So when we evaluate f prime of x at g of x, okay, we just put g of x in for x up here, and we have n times g of x raised to the n minus 1 power, and then we multiply that by g prime of x. We go through this every time I don't use it. All right. This right here, okay, is known as the general power rule, okay? So what we have shown that if n is any real number, and g of x is differentiable. Now we're differentiating g of x, so g of x obviously has to be differentiable, okay? then the derivative with respect to x of g of x to the nth power is equal to, right? You start off, you know how you differentiate x to the n, you bring the n down in front of the x, but this time we're bringing it down in front of the g of x. We subtract 1 from the exponent, just like with the power rule, but then we got to finish it off by multiplying it by g prime of x, the derivative of the inner function. So the chain rule always ends with the derivative of the inner function, g prime of x. It always ends with the derivative of the inner function, okay? That's what makes it different from the other rules in section 3.1, okay? So this is called the general power rule. And so we don't have to do the decomposition and stuff all the time, right? Once we know this rule. Okay. So as an example, we're going to find the derivative of y with respect to x if y is equal to the square root of x squared minus 5x plus 1. Well, you know, taking square root of something the same as raising it to the 1/2 power, right? So this is equal to x squared minus 5x plus 1 raised to the 1/2 power. So to find the derivative of y with respect to x, right, our inner function is this inside parentheses here. So using the general power rule, the derivative of y with respect to x, you bring the exponent 1/2 down in front of the left parentheses. And then you subtract 1 from the exponent, just like with the power rule. 1/2 minus 1 is minus 1/2. And then the last step is to multiply by the derivative of the inner function. And the inner function is what's in parentheses here. Derivative of x squared is 2x. Derivative minus 5x is minus 5. Derivative plus 1 is 0. And now you don't have, right, you don't have to do the Leibniz notation. You don't have to do what's an inner function, what's the outer, you know, all that stuff, right? You know the rule. You know the pattern, okay? So when you have something like this, right, the g of x, a function raised to the nth power, right, you just apply the general power rule. Okay? All right. Sean?
Yes.
This is a good test question, okay? So we're going to find f prime of x if f of x is equal to 2x minus 3 to the 4th power times x squared plus x plus 1 to the 5th power. Now there's more than one rule of differentiation we've got to apply, right? What's the one that we got to apply right off the bat? Yeah. Who said that? Yeah. We have a product of two functions here, right? 2x minus 3 to the 4th is the first function. X squared plus x plus 1 to the fifth is the second function. We have the product of two functions. So even before we apply the general power rule, we got to recognize we're going to have to use the product rule in finding this derivative. Right? Now, remember there's like 8 different representations for the product rule. Okay. So the one I used is derivative of the first times the second function plus the derivative of the second function times the derivative of the first. Okay. So f prime of x, derivative of the first function. We gotta finding that derivative. That's not x to the fourth, right? We gotta use the general power rule. And the derivative 2x minus 3 to the fourth power by the general power rule. You bring the 4 down in front of the left parenthesis. Subtract 1 from the exponent. And then multiply that by the derivative of what's inside the parentheses. Derivative 2x is 2. Derivative minus 3 is 0. And now you got to multiply that by the second function. The second function is x squared plus x plus 1 to the fifth. So that's the first half of the derivative. Now you got to add. We're going to multiply, add, and now we got to find the derivative of the second function. Well, second function is x squared plus x plus 1 to the fifth. So we got to apply the general power rule in differentiating this. Bring the 5 down front of the left parentheses. Subtract 1 from the exponent. Now multiply that by the derivative of what's inside the parentheses, right? By the general power rule. Derivative x squared is 2x. Derivative plus x is plus 1. Derivative plus 1 is 0. And now you got to multiply that by the first function. What's the first function? 2x minus 3 to the fourth power. This is a typical exam question.
Leave our answer like that.
Yeah, and I would put on there you don't have to simplify. Because I got to grade it. And if everybody's simplifying, there'll be 50 different answers. Yeah. So, yeah. So on these types of questions, I say don't simplify. You write out the first pass and stop. Okay? And that makes it easy to grade if everybody has this for an answer. You guys start simplifying, and then I got to check all the simplification, right? But do you understand we use the product rule in combination with the general power rule? Okay? And then we also used other rules, right, from section 3.1 and differentiating the inside of the parentheses, right? So we're applying all these different rules. And you'll have a little bit of this on the WebAssign homework, okay? Any questions on this? Okay. All right, so let's move on to the natural exponential function. We're not going to come up with write out the chain rule for every type of function, but we'll cover the major ones. Okay. So remember the derivative of the natural exponential function. One of the easiest to remember. Derivative e to the x with respect to x is e to the x. But now we're going to find h prime of x if h of x is not equal to e to the x, but e raised to a function of x. Okay? So when we decompose f(h) of x, our outer function f of x is e to the x, and g of x is our inner function. Right? G of x can be any differentiable function. Okay? That's our inner function, right? We're doing a general formula. Okay? So we're not specifying algebraically what g of x is equal to. We just know it's differentiable. Okay? When we have that decomposition, then h of x, which is equal to f of g of x, is equal to, right? F of x is equal to e to the x. So when you evaluate f at g of x, you put g of x in for x up here, and you have e raised to the g of x power. F prime of x, the derivative of f of x, is just e to the x, right? So, from definition, derivative of the composite function, h prime of x is equal to f prime of g of x times g prime of x. Well, f prime is equal to e to the x, right? So let's do it step by step. So g of x, so f prime is equal to e to the x. So f prime of g of x, which put g of x in for x on the right hand side. And we have e raised to the g of x power, then times the derivative of g of x, which is g prime of x. So the derivative of h of x, e to the g of x, is itself, just like derivative e to the x is itself. Derivative of e to the g of x is itself times the derivative of the inner function, g of x. Remember, in chain rule, you always end with the derivative of the inner function. Okay? So, we can conclude the derivative with respect to x of e raised to the g of x power is itself times g prime of x, the derivative of the inner function. Okay? So let's find f prime of x if f of x is equal to e raised to the tangent x power. Okay? Tangent x is a differentiable function, right? Except at its points of discontinuity. Okay? Well, from the derivative, right, from up here, the f prime of x, right, derivative f of x is equal to itself, e tangent x, times the derivative of tangent x. What's the derivative of tangent x?
Secant squared.
Secant squared x. And this test question, you probably stop right there, but I don't like ambiguity, so if I switch the order of multiplication and write secant x squared times e raised to the tangent x. Both answers are sufficient. They're fine. Okay. Any questions on that? Okay. All right. Now, for those of you who took pre-calculus, probably get tired of me picking on you. But we also, in addition to studying the natural exponential function, right, we study exponential functions in general, a to the x, right, where a is greater than 0, not equal to 1, right? So, the derivative of any exponential function, not just the natural exponential function. Hey, riddle me this, pre-calc students. What's the, if I have f of x is equal to a to the x, a is greater than 0, not equal to 1. What's the inverse function for a to the x? Are you raising your hand?
No.
No, you're raising your hand. Huh?
I don't know.
You remember? Did you take pre-calc here?
No.
Did you place first year out of high school? Sean, do you remember?
Can't remember.
Sean?
Nope.
4 of my pre-calc students. Anybody other pre-calc students of mine in here? Raise your hand. It's the log function, base A. F inverse of x is log base A of x, right? Just as if g of x is equal to e to the x, then the inverse function of e to the x is the natural log function, right? Yeah. The review is always a good thing because that's how you get it burned into your brain. Okay. All right. So the derivative of any exponential function, right? A to the x, a is greater than 0, not equal. Now, those of you placed in here at high school, you had to have studied logarithms in high school, right? I'll admit I had a hard time with them. It was something that did not come naturally to me. Yeah. All right. So the derivative with respect to x of a to the x, well, you know, the derivative of e to the x is e to the x, right? So you might suspect derivative of a to the x is a to the x. But we have to multiply it by one more thing. And it's the natural log of a, the base a. Okay. And if a was equal to e, we had e to the x, then we have the natural log of e over here. And what's the natural log of e equal to? 1. That's why you don't see it in the derivative of e to the x, okay? Because the natural log of e is equal to 1, okay? All right, so now for the chain rule, right? We have the derivative with respect to x of a raised to the g of x power, right? So with chain rule, right, replace x with g of x. So based on what we know, What do you suspect the derivative of a to the g of x is going to equal? What's the first term? A to the g of x. The second term, natural log of a. And what do you think the third term is? G prime of x, right? Chain rule always ends with g prime derivative of the inner function, right? So this is the derivative of a to the x. This is the derivative of a raised to the g of x power. Okay. All right. Well, we'll show a couple quick examples tomorrow, right? I think we ended 20 after, right? So 7, 10, 14, 17, 21, 25. And Hannah is the one we're missing. Okay. So I'll see you tomorrow.